Hello friends. So as the last module of this course on conductive heat transfer, today we will be looking at boiling. In the previous two classes, we were looking at convection with phase change, and we were looking at condensation as the mode of phase change. So we looked at what is called the film condensation, where the condensing liquid actually completely wets the surface on which it is condensing, and it forms a film on top of the surface, and the film flows downwards like a boundary layer, as we had studied boundary layers in single phase flows. And then we looked at the heat transfer characteristics in film condensation. So we were able to at least develop a theory of a certain form, and it was a theory which is quite similar to the theory that we did in boundary layers of single phase substances, and we were able to predict the form of the Nusselt number expression, and we used integral method or simple temperature profile assumptions in order to get the Nusselt number correlation. But in contrast, we found that in drop phase condensation, such a theory was not possible, unified theory was not possible, because of the complexities that is there in the process and the unsteady nature of the process itself. Therefore, we depended completely on empirical correlations, the compilation of experimental data over several decades. Many people's experiments were put together, and correlations were derived from those experimental data. In boiling also we would have a similar approach. We don't really have a unified theory of boiling heat transfer, and therefore we would be using empirical correlations to the extent they can be used. But again, the empirical correlations, particularly with phase change, are not enormously accurate, but they would be reasonably okay with respect to engineering calculations. Now with that background, if we look at heat transfer in boiling, so in order to study heat transfer in boiling, we normally look at boiling with respect to two kinds of classifications. One classification, of course, is the nature of the boiling, nucleate boiling, and film boiling. So nucleate boiling is where you have the liquid in contact with a superheated surface, the surface which is at a temperature higher than its saturation temperature. So on the surface, because of the heat transfer, the liquid starts evaporating in nuclei, and these nuclei normally are formed at various surface imperfections that are there, cracks on the surface or small lumps or bumps on the surface. So micro imperfections that are there on the surface, or even macro imperfections on the surface, they become the nucleation points, or the points at which the first vapor bubble actually arises, and this vapor bubble then grows in size, and once the vapor bubble is large enough to be either taken away by buoyancy or by the flow that is happening on top of it, getting swept away. So the bubble detaches itself from the surface and goes into the bulk of the liquid, and a fresh nucleation again starts in the nucleation site. So you have discrete droplets. So if I have a surface like this, there are nuclei that are formed on the surface, and suppose this is the top surface of the liquid. There are two possibilities. One is that the temperature of the liquid is less than the saturation temperature, and the other is temperature of the liquid is greater than the saturation temperature. Okay, so in case when the temperature of the liquid is less than saturation temperature, what happens is once this bubble gets formed, this is T wall greater than T sat. Okay, so there is a superheat at the surface, and therefore the vapor bubbles are formed there. And once the vapor bubbles are formed, they get detached. And let us look at only natural convection now. So suppose this is the direction of gravity. So these bubbles, because they are lighter, they just rise up, and the natural convection, because of the buoyancy, because of the temperature, the density difference between the liquid and vapor, gets these bubbles to rise up. Okay, and when the T liquid is less than T saturation, as the bubble goes into the liquid, it starts condensing around its periphery because the liquid is cooler, and eventually the bubble disappears. It becomes smaller and smaller and disappears. So the bubble collapses. Okay. So if you have got a liquid whose bulk is at temperature which is less than the saturation temperature, and the surface is at a temperature greater than the saturation temperature, then what happens is the bubbles that are getting released from the nucleation sites, they get nucleated and they grow big enough, and then because of buoyancy they get detached. And once they get detached and go into the liquid, all the surrounding liquid is at a temperature which is lower than the saturation temperature. Therefore the condensation of the vapor starts around the periphery. So around the bubble, because the liquid is cooler, the condensation happens. Then gradually the bubble becomes smaller and smaller. Eventually it disappears. So that is called the collapsing of the bubble. So this happens in the case of nucleate boiling in the presence of liquid at temperature less than its saturation temperature. But in case the liquid bulk is entirely at its saturation temperature, which happens after some time, because these bubbles go and condense into the liquid and give away the latent heat of vaporization to the surrounding liquid, the liquid temperature goes up. So eventually at some point the whole liquid actually becomes T liquid is equal to T sat. Sorry, it cannot be greater than T sat. The entire liquid temperature becomes equal to saturation temperature, in which case then the bubbles that get detached, they continue to move because the surrounding liquid is also at saturation temperature, because of which there is liquid vapor equilibrium all along the liquid vapor interface around the bubbles. And so these bubbles just go, and finally the bubbles are released into the atmosphere from the free surface of the liquid. Okay, so this is basically saturation boiling. So here this is called subcooled boiling. And this is saturation boiling. Okay. So in saturation boiling, the vapors don't condense in the bulk of the liquid, but they just continue to rise up because of buoyancy and eventually come to the free surface, and the vapor is released into the surroundings. Okay, so there is vapor loss from the top surface of the liquid. So this is what happens in saturation boiling. Both of these come under the category of nucleate boiling because there are nuclei of the bubbles which are not combined or joined with each other, but they are discrete events happening separately at different points on the surface. As this temperature difference T wall minus T sat goes on increasing, what happens is the number of nucleation sites also goes up, and the number of bubbles that get formed become much larger. So then the bubbles start coalescing with each other and start becoming larger and becoming slugs. Okay, slugs, or sometimes those slugs, they are big columns, they just get added to each other. Okay, so you have slugs or columns of vapor, okay, where the vapor presence becomes much more on the liquid surface, which is the case that happens when the T wall minus T sat goes on increasing. Okay. So eventually we reach a certain state where these slugs or columns become widespread all over the surface, then you get what is called a film boiling, where this is T wall greater than T sat. Okay, there is a reasonably continuous film of vapor that starts forming on the surface, and then there are slugs and columns of vapor that escape from above this. So this is the liquid surface, let us say. So this kind of a boiling, where there is a vapor film which is stably formed between the liquid and the solid surface, is called film boiling. Okay, so what happens because of film boiling, therefore, because the vapor has a much lower thermal conductivity as compared to the liquid, the heat transfer rate between the wall and the liquid starts coming down, and the wall temperature starts rising much more rapidly with the same amount of heat that is given, because the heat transfer from the wall to the evaporating liquid decreases, and therefore the rate of evaporation goes down, the heat flux goes down, and the stable vapor film gets established in between, and the wall temperatures rise. For the same heat flux or a reduced heat flux, the wall temperature increases. Okay. So this is what we call as film boiling. So when the nuclei are separate, it's called nucleate boiling, and when nuclei merge together and form a stable film, where heavier liquid is standing on top of a lighter vapor column reasonably stably, because of the rate at which vapor is formed, we get what is called film boiling. And as the film boiling, as the heat flux is persisted, and the rate of vapor formation increases, and the stable vapor is there, and the liquid surface goes up. The solid surface temperature goes up. The temperature difference between the solid surface and this is always at Tsat, because it's boiling. So the temperature difference between T wall and Tsat goes on increasing. Then you get strong radiation heat transfer that starts happening between these two, and the heat transfer recovers again. Okay, so you get an increasing rate of heat transfer. So in nucleate boiling, initially you have low heat transfer, and the heat transfer goes on increasing as T wall minus Tsat is increased to reach a maximum. And then after that, once film boiling sets in, the heat transfer rate or heat flux comes down, but the temperature difference between the wall and saturation goes on increasing. And after that, there is a recovery because of radiation heat transfer, and the heat flux starts increasing again. So this is the form in which the curve is. I'll draw the curve and explain the various parts of it separately. So all of this we have actually talked about where there is no flow of the liquid is stagnant, so it is called natural convection boiling, or we call it pool boiling. Why is it called so? Because there is no mechanism of forcing the fluid on top of the solid surface, so there is no flow of fluid, the flow of the liquid on top of the solid surface. The liquid is stagnant in the form of a pool, and therefore it's called a pool boiling. And primarily the vapor bubbles rise up because of natural convection, and that is a mechanism of heat transfer, so it is called the natural convection boiling. So the other classification is the flow boiling, where there is a flow of liquid on top of the solid surface, and therefore there is a combination of both natural convection trying to lift up the bubbles from the surface, and the flow trying to sweep away the bubbles from the surface. So you get the flow boiling can be classified in two forms again. So you can have mixed convection boiling, so where the natural convection is also present, that is taking the bubbles away, and the forced convection is also present, and both of them have comparable strengths, then you call mixed convection boiling. And in the case where the flow is much stronger as compared to the natural convection, then you get what is called the forced convection boiling. So G is neglected, that is the natural convection heat transfer component can be neglected as compared to the forcing condition or the flow conditions, whereas here G is important. Okay, so these are the classifications of boiling that we can talk about, and flow boiling can also have nucleate as well as film boiling, because while there is a fluid flowing on top of a superheated solid surface, the mechanism of bubble formation can be in the form of nucleate, where the discrete bubbles are formed and then they are swept away by the flow or natural convection. So that is the nucleate flow boiling. And you can also have film flow boiling, where there is a stable film of vapor that is formed on the surface of the solid, and you have film boiling. Okay, so common examples where nucleate boiling is used are power plant boilers. So for those of you who won't know what the power plant boiler is like, in the power plant boiler you have a furnace and the walls are lined with tubes. Okay, so you have the combustion happening in this region and the heat transfer to the walls happens, and the walls actually have vertical upward flow, so there are headers of supply water which comes from the economizer. The water that comes from the economizer goes into the headers, and from the headers the water is connected to the vertical thing. So these are called risers. Okay, so the pipes that are going upwards are called risers, and then you would have what is called a boiler drum at the top of the boiler, and from there you would have pipes that come downwards and connect to the headers that are there. So this pipe is called the downcomer. Okay, so in a boiler typically you have a drum and you have the entire water wall. You call these as water walls. Because you don't want the walls of the furnace to face the heat, but you would like that heat to be absorbed by the water. And at the bottom you have the headers. So from the drum you connect downcomers all the way to the headers here, and from this the water rises and goes back to the drum. Okay, so there is a circulation of water that happens here. So this is the direction in which the water circulates, and there is a furnace here from which heat transfer happens to the water walls. So in these tubes there is water flow which can be forced by pumps, or which can be just driven by this natural circulation, because there is a big temperature difference and big difference in vapor content. So the water with vapor content is lighter, it rises, and water without the vapor content is lower. So there is a circulation, and usually you get if m dot v is the rate at which vapor is formed in this boiling, then the total flow rate is between 6 to 7 m dot v. So 1/6 or 1/7 of the water that flows through the pipes typically evaporates in the case of a power plant boiler. So this is a very ready example of forced convection boiling, forced or mixed convection boiling, where the water circulation is maintained by pumps. It's a forced convection boiling, and where there is a natural convection circulation, it's a mixed convection boiling. Usually it's a mixed convection boiling in most power plants, because the height of the boiler from the drum to the header typically is anywhere between 30 to 75 meters. Okay, so it's quite a tall area. So the amount of natural circulation force that you get from the height of the, so this is a cold or liquid column, and this is the liquid vapor column. So the liquid vapor column is always lighter and rises, and the flow gets established by natural circulation. So there is always either a mixed or forced convection, sometimes even natural convection that happens in these boilers. So in this one, the heating inside the pipes actually happens through either forced convection boiling or mixed convection boiling. It is a flow boiling example. Okay, Another example is evaporators in refrigerators or ACs, where you have a tube inside which the cold refrigerant flows, and this surface is finned surface which is exposed to the air that is flowing on top of it in the case of an air conditioner, or in the case of a refrigerator there are no fins quite commonly, but you have this freezer whose walls are lined with this evaporator tubes, so there is heat transfer from the cabinet to the walls of the freezer, and this liquid that is going here evaporates, and you have liquid vapor mixture that is going out here. So here also most commonly the nucleate boiling is employed. In some cases where vigorous boiling happens, this transitions to film boiling, but normally one tries to avoid film boiling in these things because film boiling has lower heat transfer coefficient. But wherever the temperature differences between the surface and the refrigerant are very high, some fractions of the tube also experience film boiling, but most of the time it is nucleate boiling. Okay, so these are examples. And simple boiling of water in a beaker. So you have a burner in a gas stove, and you put a chai ka patila where you want to boil water for tea or boiling water for cooking. Then this typically is nucleate boiling. Initially it is natural convection boiling. There is circulation that happens initially by natural convection, and when the temperature of the heated surface tries to increase further, then you get the nucleate boiling. So the boiling that you observe in the cooking vessel in the kitchen is usually nucleate pool boiling. So it is no flow boiling, but it is nucleate pool boiling. Okay, so that is the thing that you commonly see. So these are examples of these boiling situations that we commonly encounter in practice. Now let us go to the diagrammatic representation of the nucleate pool boiling process. Okay, so let's plot this. Okay, in study of boiling, primarily we would like to establish the relationship between the heat flux Q dot wall and the superheat temperature of the wall T wall minus T sat. Okay, so we would like to get the relationship between these two. In fact, the ratio of these two is your heat transfer coefficient H bar. Okay, so Q dot wall, the average heat flux over the entire wall surface, divided by the temperature difference between the wall and the saturation temperature, gives you the heat transfer coefficient. So the boiling curve that we normally plot is Q dot wall in watts per meter square, okay, against the superheat temperature, which is T wall minus T sat in Kelvin. Okay, so this is a log plot. So let's try to do that. Let's say this is 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, 10 to the power of 6. So these are in watts per square meter. So it's the fluxes range from anywhere like a few hundreds to a couple of millions of watts per square centimeter, square meter, sorry. And this temperature difference, let us say it starts from, let's say 0.2, let us say this is 1, let us say this is 10, let us say this is 100, let us say this is 1000. Okay, so it's a logarithmic scale that we are looking at. Significant things that we need to note are something like 4 degrees Celsius, something like 30 degrees Celsius, something close to 200 degrees Celsius, and about 1000 degrees Celsius. Sorry, the temperature differences in Kelvin or Celsius, these temperature differences are significant. Why? Up to about 4 degrees Celsius temperature difference, you have a regime which is called the natural convection boiling. So the heat flux increases. What I show is very nearly a straight line in the log, so it's actually quite an exponential increase, right? So up to about 4 degrees Celsius, you have what is called the natural convection boiling. What is natural convection boiling? In natural convection boiling, you have a surface and the liquid standing on top of it, let us say. There is no bubble that is formed on the surface, but because the hot surface, hot liquid that is at the surface becomes equal to the wall temperature T wall greater than T sat, but the temperature difference is still under 4 degrees Celsius, then the hot liquid, which is reaching temperatures which are greater than saturation temperatures, still vapor bubbles are not formed. Because of the higher temperature, the liquid rises up because of natural convection, and cold liquid from elsewhere and comes and replaces it, and you get natural circulation bubbles or natural convection loops that are there. Okay, natural circulation loops are formed. So this is the mechanism of heat transfer in the first 4 degrees of temperature difference that you typically see. Then from about 4 degrees Celsius up to about 30 degrees Celsius, okay, at 30 degrees Celsius you reach a heat flux which is a few million watts per meter square. Okay, so this is called the Q dot max. Okay, so this is quite a steep rise that happens, and this part is called the nucleate boiling. Okay, so nucleate boiling is the place where the heat transfer coefficients are substantially higher. See, you can see 10 to the power of 4 is typically the value of heat flux at 4 degrees Celsius temperature difference. So the heat transfer coefficient, if I calculate using this, here the H in this point is of the order of 10,000 by 4, which is around 2,500. Okay, so H is about 2,500 in this location. It gradually increases from here to here. Okay, or remains of that order. In natural convection boiling, the heat transfer coefficients are of this order, about a few 100 to a couple of thousands watts per meter square Kelvin. Okay, whereas if you look at the location where I've marked it as Q dot max, which is what is called the critical heat flux, which is the highest heat flux that you get in nucleate boiling, that is of the order of, let's say, 10 to the power of 6 or 2 into 10 to the power of 6 divided by 30. Okay, so it is something like 200 by 30, somewhere like 6 into 10 to the power of 5. Okay, so in the second part, this location, it's about H is of the order of 6 into 10 to the power of 5 watts per meter square Kelvin, which is very, very high as compared to what is there in the natural convection boiling region. Okay, so this is what we call as the critical heat flux. Why is it called the critical heat flux? Because we said that the bubbles are small and discrete in this region, and as you go higher with T1 minus T sat increases, the bubbles become slugs and columns, and they merge with each other, and eventually after this point the heat flux starts coming down because there is a stable film of vapor that gets formed after that. So from here until about 200 degrees Celsius of superheat, there is a decline in heat flux, and the heat flux comes down to around again 10 to the power of 4. So this is Q dot double prime min, and the temperature at which the minimum actually happens is typically called the Leidenfrost temperature. And for this plot I am doing for water at P atmospheric, okay, at atmospheric pressure. So the value of Leidenfrost temperature is about 200 degrees Celsius above the saturation temperature. Okay, so that is typically what you see. So typical way to visualize the Leidenfrost temperature is if you have seen hot tawa, the roti ka tawa, chapati ka tawa that is kept on the gas stove and the flame in full force, then the typical temperatures of the tawa go from anywhere between 200 to 350 degrees Celsius, right? Depending on how strong the flame is, the temperatures go as high. So if the temperature of the tawa is close to about 300 degrees Celsius, and if you just put a drop of water on the tawa, you would see that the drop of water would not be stable, but it keeps running around. Why is it running around? Because under the water there is a stable vapor film which will support the water. The whole liquid drop is actually floating on top of the vapor bubble, and therefore it just keeps running around because the nucleation happens very vigorously, and therefore there are forces exerted on this bubble, and the bubble cannot stay put, it just keeps running around. That happens in this region around the Leidenfrost temperature. Okay, so this is something that will be easy for you to remember. Whenever you see a droplet of water running around on a hot tawa, you can remember Leidenfrost temperature. Okay? That's the point. So that is the point around which the Q is minimum. Again, you can see this is 10 to the power of 4, right? The heat transfer heat flux is of the order of 10 to the power of 4 watt per meter square, and the temperature difference is of around 200 Kelvin. So it is 10,000 by 200, it's about 50, right? So H comes down to almost 50 watts per meter square Kelvin, right? So it decreases from something like 6 into 10 to the power of 5 watts per meter square Kelvin to about 50. So this diagram is highly deceptive because it is on the log scale, and the curves look so beautiful, but if you actually put it on the linear scale, these curves look very enormously, horrendously shaped, and therefore there is a drop of almost 4 orders of magnitude in heat transfer coefficient from here to here, right? The heat transfer coefficient comes down by a factor of more than 10,000 from the Q max to Q min. After this is when the film boiling is stable and radiative heat transfer picks up, because the temperature difference between the surface and the liquid is large enough. So the radiative heat transfer picks up, and then the flux starts increasing again, and close to about 1000 Kelvin difference, this reaches somewhere close to this. Okay, so this is the way the thing goes. So beyond a superheat of about 1000 Kelvin, the heat fluxes in film boiling can exceed the critical heat flux and go up further. Okay, so this leg, the left leg, is the natural convection and nucleate boiling leg, and this right side leg is the film boiling leg. So the heat transfer analysis of boiling typically deals with one part, which is the nucleate boiling leg, which deals with this side of the curve, and the other set of correlations which deal with this side of the curve, because the phenomena are completely different from this side to this side. The second thing that one needs to understand is that this curve, if I want to generate experimentally, it is not possible in a straightforward manner. That is something which the first person who experimented with this nucleate pool boiling curve is attributed to Nukiyama, Japanese scientist. So this is called the Nukiyama's curve, or the Nukiyama's pool boiling curve. So this curve, when it was initially generated, Nukiyama tried to have an electric heater, and with the electric heater he tried to heat the water to get to here. So what happened was, he was able to get through starting from here he was able to get through from here to here, but when he reached here, the coil that he used for electric heating or water would just burn out. So it's called the burnout point. Okay. So Nukiyama was not able to get beyond the critical heat flux point, because when he tried to heat further, because the temperature of the wall went beyond the saturation temperature. So water saturation temperature is like 373 Kelvin or 100 degrees Celsius, and if the temperatures go about 1000 degrees beyond that, so it's about 1100 degrees Celsius, the heater material he was initially using nichrome. Nichrome would melt temperatures under 1100 degrees Celsius, and therefore he would not have the heater continuing to heat this thing. So what Nukiyama did was to replace nichrome coils with platinum coils. Platinum heater, because platinum has a melting point which is more than 2000 degrees Celsius. So he thought that he would be able to get that nicely. So what Nukiyama ended up getting was, he got until here, okay, up to the point which is critical heat flux, and from there was a sudden jump and the temperatures jumped to this value, and from here he got this curve. Okay, so he heated from here and it suddenly jumped here, and then the temperature differences went beyond 1000 Kelvin and he got this curve. So this is something that he did. He tried to say, okay, there is a discontinuity here, because up to here I was able to measure temperatures, and from here I am able to measure temperatures, but here there is a quick rise in temperature and I am not able to measure any temperatures. So he thought that there is something in between these two. So he said, okay, let me try to cool it. When he tried to cool it, he was able to get below this point, all the way up to Leidenfrost temperature. Okay, up to here he came, and at Leidenfrost temperature the entire boiling collapsed, film boiling collapsed, and he suddenly jumped to this point and he started coming down from here. Okay, so Nukiyama, when he tried to use the platinum heater and electrically heated the water, so he had let us say a tank of water, and he had a coil and he impressed the voltage across this, and this was a platinum coil, and he did it. So he was able to measure the temperatures of the coil and the water around and do that. So he was able to get this part of the curve, which is the nucleate boiling curve, and this part of the curve, which is the film boiling curve while heating. While cooling, he got all the way here, but then it jumped here and back here. So some in between these two, the downward part of the curve that we drew here, this part of the curve, which is called the transition boiling, he was not able to get. Later, a pair of German scientists tried to use, instead of electric heating, they used temperature controlled heating process. So this is flux controlled heating. Because by controlling the current through this coil, you will be able to control the heat flux, because the heat flux is nothing but voltage into current that is dissipated in this coil divided by the surface area of the coil. So you can control the flux by controlling the current and voltage that are impressed on the platinum coil. So this is a flux controlled heating. Instead, when you did temperature controlled heating, where you controlled the T wall precisely, so it didn't jump directly from this delta T to this delta T, but it started coming down. So they were able to get the curve in the form that we did. So here, and after that it came down and then it went up. So they were able to do this and this and this, and in the experimentation backwards also they were able to get this. So this they did by having a tank of water and passing, let us say, steam through this, and by adjusting the state of the steam and the flow rate of the steam through this, they were able to precisely control the temperature of the surface, and therefore T wall minus T sat was more precisely controlled, and they were able to get the entire curve. So this transition boiling region is actually an unstable region. It doesn't stay stable unless you maintain very specific temperature difference conditions, and only when you do that using the temperature controlled heating, then you get that part of the curve. Otherwise, you get the nucleate boiling and the film boiling parts very easily, but the transition boiling is unstable, and therefore in most naturally occurring systems, or even most engineering systems, the transition boiling phase is normally not encountered. You either have nucleate boiling or film boiling, but the transition boiling is a very quick phenomenon. It just moves off and it goes from one form to the other. So these two are the stable boiling mechanisms that are commonly encountered. Okay, so once we have understood the descriptive story of how the boiling happens in nucleate boiling and film boiling, and we also understood the regimes of natural convection and forced convection or mixed convection boilings. Now we can look at the correlations that exist. So the correlations that exist can be divided, as I told you, in two parts. One part which looks at the natural convection and nucleate boiling region, and the other part that looks at the film boiling region. So we'll look at them closely from now on. So nucleate boiling and critical heat flux. Critical heat flux is quite frequently abbreviated as CHF. Okay, so the correlation that is even used today is because of the arduous work done by Rosenau. So Rosenau's group basically went through all the experimental data that they had generated, as well as the data that were available until then from various experiments, and based on a very large body of data, they correlated T-wall minus T-sat to Q-wall double dash. So T-wall minus T-sat is equal to HFG, which is basically latent heat of vaporization, divided by Cp of the liquid, multiplied by liquid Prandtl number raised to the power of S. This is one constant that the correlation obtained using fits on experiments, and another constant CSF, which is another model constant. These are the two things that one needs to look at for different substances and situations. Otherwise, the form of the equation is quite familiar. Q dot double prime at the wall divided by mu liquid into HFG multiplied by the surface tension coefficient sigma divided by G into the density difference rho L minus rho V. This whole thing raised to the power of half, and this bracket raised to the power of 1 by 3. So this is the curve that Rosenau fitted. In this, S is equal to 1 for water and equal to 1.7 for organic liquids. So most of the experiments were either performed using water or organic liquids like alcohols, alcohols like ethanol, methanol, and various other organic substances such as refrigerants, carbon tetrachloride, chloroform, or various organic liquids of that kind, and R12, R4, R22, various kinds of organic liquids. They were the ones that were used for most of the experiments. So what Rosenau found is the exponent of Prandtl number was 1 for water and 1.7 for organic liquids for the experimental data to fit into this curve. And CSF actually depends on the liquid surface pair. Okay, so this is the empirical information that needs to be built into the system. So, for example, if it's a stainless steel wall with water, or if it is copper wall with water, if it is stainless steel wall with R22, copper wall with R22, copper wall with CCl4, and so on, the pairs had different values of CSF in the range of 0.001 of that order. Right, the CSF values for most substances, this 0.001 to 0.01 order, so 10 to the power minus 2 minus 3 order is the value of the CSF. It's a non-dimensional constant. So this is the thing that they were able to fit. Okay, so now this is the thing that Rosenau found, and one interesting thing they found is that it is independent of geometric configuration. Which is a very interesting thing, that whether it's boiling on a flat surface, boiling on the surface of a tube, boiling on the surface of a sphere, boiling on any other surface, the geometric configuration didn't seem to matter. So long as the other parameters are known, we were able to get the relationship between T wall minus T sat and Q wall double prime. Okay, but then it's only to engineering approximations. This word engineering approximation is a very interesting word that is used in many contexts. When you are not able to get precise values within 5 to 10% accuracy, but you are able to get values which are about that order, let us say 50% error, 100% error, 25% error, 30% error, you say that it's valid within engineering approximation. So basically, in engineering, we normally work with factors of safety. So we normally use a factor of safety of 1.2, 1.4, 1.5 in cases where the parameters are more precisely known, and where the parameters are less precisely known, you work with a factor of safety of, let us say, 2 or 3 sometimes, so that things are designed for safe functioning. So engineering approximation basically means here that the accuracy is not very good, right? So let us understand this. So if Q dot wall is known, then this equation gives T wall minus T sat from Rosenau is within about 25% of experimental data. Okay, so the accuracy or the deviation from experimental data is about 25%. So let's say if this predicts that the temperature difference is 15 degrees, so the temperature difference can be anywhere between, let's say, 12 degrees to 18 degrees or 20 degrees. So that is the kind of accuracy that you get with this one. Okay, remember that the range of T wall minus T sat for this is under 30 for water, right? So if you work with 0 to 30 degrees temperature difference between the wall and the saturation. So the wall temperatures at atmospheric temperature, if the saturation temperature is approximately 100 degrees Celsius, then the wall temperatures up to 130 degrees Celsius is what is covered by this correlation. And here the temperature difference comes within 25% of experimental data. So if you predict the temperature difference and compare it with experimental data, the deviation can be up to 25%. Okay, so that is the thing that you get. But if the same equation is reversed, so if I know the value of T wall minus T sat and I want to get the value of Q wall, you see that this becomes a more complex expression, and because the curve itself is such a S-shaped curve on log-log scale, right? The accuracy with which it can be respected is affected substantially. So if T wall minus T sat is known, then Q dot wall predicted by Rosenov equation is within 100% of experimental data. Okay, so this is much more serious because you see that the Q wall is in the order of 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, 10 to the power of 6. So if I predict, let us say 20,000, the values can well be anywhere from 10,000 to 30,000 or something like that. Almost up to 100% deviation can be there, right? So that is the approximation that is there. But then you say that, all right, we'll then work with factors of safety if I have to design for this. Okay. So particularly, for example, if I am looking at power plant boilers, if film boiling starts happening on the tube surfaces, then the tube surface temperatures can go well above the melting point of steel, because the furnace temperatures are about 1700, 1800 Kelvin, or maybe higher than that, 1700 degrees Celsius, and therefore about almost 2000 Kelvin. Then the if we enter the film boiling regime, the temperature difference between the wall and the steam, actually the power plants operate at about 150, 200, 250. Nowadays we have even supercritical boilers. But let us talk about boilers in which boiling is happening. So if the temperature difference, if the pressure of operation is like 200 degrees Celsius, at which the boiling point is almost 300 degrees Celsius, okay, at 200 atmospheres, at 200 atmospheres of pressure, the boiling point is close to 300 degrees Celsius, then the 1000 degree superheat would actually mean 1300 degrees Celsius on the wall. So 1300 degrees Celsius is the temperature at which any steel would become softer, and therefore, and it's not economical also to build power plant boilers using expensive tube material, because in a typical power plant it is known that the length of tubes can be anywhere between 3 to 5 kilometers. That is the length of tubes that are commonly used. So the cost of the boiler will become substantially higher the moment you try to use materials which are more expensive, and therefore you need to work with a substantially better or substantially higher factor of safety, right? So you should make sure that the flow rates of water are sufficiently high that at any given point in time no part of the tube wall would run dry. Okay, so you need to make sure that the water is always in contact, liquid water is always in contact with the tube walls, so that there is no film boiling that is starting to happen, and therefore there is no tube wall temperature that goes to excess. And in order to estimate what would be the tube wall temperature, you can use this, but yeah, so you can use this actually, where the heat flux can be estimated and T wall minus T sat can be evaluated. And if you see that this Q wall goes anywhere close to the critical heat flux, you try to increase the water flow rate and bring it down, so that you work safely in the lower part of the nucleate boiling curve and don't get too close to the critical heat flux region, beyond which the film boiling would start happening. Okay, so that is what basically we mean by engineering approximations, and what we need to take care when we are using the correlations that are available for nucleate boiling and critical heat flux. For large horizontal surfaces, so where we mean large, where the bubble size vis-a-vis the size of the horizontal surface, this let's say L, and let's say this is a diameter of D, okay, L is substantially greater than D. This is what we mean by large horizontal surfaces. It's not that geometrically they are very large, but even your kitchen patila, in which the bubbles are of the order of a couple of millimeters diameter, and the vessel is about 10-15 centimeters diameter, the L is much larger than D, so her large horizontal surfaces can be used even there, right? So for large horizontal surfaces where the surface is much larger as compared to the size of the bubble, we can use a correlation which is simplified as compared to this, which will be the critical heat flux Q max is equal to 0.149 multiplied by HFG into rho V to the power of half, okay, multiplied by sigma G into rho L minus rho V. Okay, so in this basically you need to recognize the symbols that are there. HFG, of course, is the latent heat of vaporization of the liquid at that pressure and temperature, and CPL is the specific heat of the liquid, PRL is the Prandtl number of the liquid, Q dot is the heat flux at the wall, mu L is the viscosity of the liquid, again HFG is the latent heat of vaporization, sigma is the surface tension coefficient, okay, G is acceleration due to gravity, and rho L minus rho V is the density difference between the liquid and vapor. Okay, so this is the symbols that we need to recognize. So the same symbols are here. HFG, rho V is the vapor density, sigma is the surface tension coefficient, G is the acceleration due to gravity, and rho L minus rho V is the density difference between the liquid and vapor, right? And so if you have look at the TS diagram of this one. So you have the liquid state here, vapor state here at any given pressure. So this is TS diagram. So at any given pressure you have the TS curve like this. This is for some particular value of pressure. Then this you will have a VF, and here you'll have a VG. Then a VF is 1 by rho L and VG is 1 by rho V. Okay, so this is how you recognize these. So VF and VG are the specific volumes at liquid, saturated liquid state and saturated vapor state, or rho L will be 1 by VF and rho V will be 1 by VG. So this rho L minus rho V is basically 1 by VF minus 1 by VG. So that is the thing that you calculate. Okay, so just to help you connect it to thermodynamics that you know. So for large horizontal surfaces, this expression is a much more simplified expression as compared to the Rosenau expression. Again, this is independent of the material of the wall and the configuration. For large horizontal cylinders, that is boiling on top of a cylinder, that is you have got a cylindrical surface and boiling is happening from the top of this, nucleus are rising. So this kind of a surface system, large horizontal cylinder, you replace this 0.149 by 0.116. Okay, the rest of the expression remains the same. Okay, so this is basically the discussion about the correlations that we use for nucleate boiling and critical heat flux. Now let us look at the other side, film boiling and Q min. So if you look at the geometric feature, film boiling on any surface, suppose I have a tube surface and there is film boiling happening on top of the tube, so then you have a stable film of vapor that is enveloping this, and this vapor bubble just tries to rise. Well, there is a liquid that is surrounding this region. This is quite similar to if I have film condensation on this one where there is all vapor all around, then there is a liquid film that is formed around this and it starts dripping, right? So these have a very close similarity, whether it's a cylinder or a sphere or a vertical surface where the film condensation would happen like this and film boiling actually would happen this way. The vapor film is here and here is the liquid film. This is condensation, vapors are here, and here liquid is here. Okay, so there is a similarity between these two in terms of the way the phenomena happen, and therefore the correlations also have quite a bit of similarity between themselves from film boiling and film condensation. Okay, so the correlations are quite similar. So for a large horizontal surface, okay, so you have Q dot min. This is the prediction of Q dot min. We'll come to the prediction of H separately, which will be very similar to these. Q dot min is equal to 0.09 multiplied by HFG rho V into sigma G into rho L minus rho V divided by rho L plus rho V the whole square, whole thing raised to the power of 1 by 4. So this you see is in a form which is quite similar to the kind of correlations that we wrote in film condensation. So if you look at film condensation, you see that the relationships look something like this. Okay, so you get a similar form of correlations when we go to H here. So let us look at horizontal cylinder. So this is external, film boiling outside an horizontal cylinder. So this geometry is what I am looking at. Okay, so if I have hot gases flowing through a tube and the tube is immersed inside a liquid bath and there is film boiling happening on the surface, then the horizontal cylinder external has a correlation which has quite a bit of similarity to horizontal cylinder film condensation. I didn't write the expression for film condensation when we looked at film condensation, so I'll write that also here and you'll see the similarity. So this is film boiling and this is film condensation. Okay, so let us look at the expression here. This is H bar D into D by kV. Okay, so you are actually looking at the Nusselt number with respect to the vapor conductivity. Okay, so that is understandable because you are looking at the conduction through the vapor and convection through the vapor that is being compared, so it is vapor conductivity. Whereas in the case of liquid, there is a liquid film, so it will be with respect to KL. Right, so that's the difference that you will see. So this is equal to 0.62 multiplied by dq multiplied by hfg prime into g into rho L minus rho V divided by kV multiplied by V nu V, which is the kinematic viscosity of the vapor, into T wall minus T sat, whole thing raised to the power of 1 by 4. Okay, in film condensation, look at the expression, that's quite interesting. HD bar into D divided by KL. Okay, this is equal to, this is 0.729 multiplied by dq hfg prime, okay, multiplied by g into rho L minus rho V divided by KL into nu L. So instead of V, it's L here, and multiplied by T sat minus T wall, because T wall is lower than T sat, so T sat minus T wall is positive, the whole thing raised to the power of 1 by 4. Don't you see that they are so similar to each other, except that constants are slightly different, and instead of vapor properties here, you calculate using liquid properties here. Otherwise, these are exactly similar for horizontal cylinder. Similarly, sphere. Okay, the correlations look very similar. The difference is in HFG prime. The HFG prime here is equal to HFG plus CPV multiplied by T1 minus Tsat multiplied by 0.4. Okay, let me just erase it and write it cleanly. Plus 0.4 CPV into T1 minus Tsat. Okay, and here it is HFG prime is equal to HFG plus 0.68 into CPL into Tsat minus T1. Okay, so you remember that this was a 3 by 8 in Nusselt correlation and it became 0.68 in Rosenbaum correlation, and that is used across the thing. So basically, when it is defined in terms of Jacob number, divide throughout by HFG. So then it becomes HFG multiplied by 1 plus 0.68 into Jacob number. Okay, so here it's very similar. It's actually, if I define Jacob number in terms of CPV T1 minus Tsat divided by HFG, then it will be 1 plus 0.4 Jacob. Right? So that's quite similar in terms of this, only the constants are different. Otherwise, the expressions look very similar. Similarly, for a sphere, in vapor in film boiling, it is HD bar D by KV is equal to 0.67 multiplied by dq into HFG prime g into rho L minus rho V divided by kV nu V into T1 minus Tsat whole thing raised to 1 by 4. And here it will be HD bar D by KL is equal to 0.815 multiplied by the same expression dq HFG prime G into rho L minus rho V divided by KL nu L into T1 minus Tsat, sorry, Tsat minus T1 whole thing is for 1 by 4. So it's the same expression. So the same Jacob number, this Jacob number applies both up and here, and this Jacob number applies both here and here. Okay, so and to clarify, the properties are all evaluated. KV, nu V and CPV at T-wall plus Tsat by 2. And the same thing can be said for this also. The KL, nu L and CPL would be evaluated at T-wall plus Tsat by 2. Okay. So that's the expression. So you see that the film condensation and film boiling correlations look very similar because of the way they behave. The condensation happens with the liquid film falling downwards, and film boiling happens with the vapor film enveloping the geometry and going upwards. So the same thing geometrically is similar, and therefore the same kind of correlations apply to both. Now, one thing that we need to understand in studying film boiling is that beyond a certain temperature difference, T1 minus Tsat, radiation starts taking precedence and becoming important. So at higher temperatures, T1 minus Tsat, radiation is important. So we need to include radiation. So what has been said is that when H rad is less than HD, you use one expression, and when it is greater than or of the order of HD, you use another expression. What is H rad here? H rad is nothing but the radiative heat transfer coefficient, which you evaluate as heat flux, radiative heat flux divided by the temperature difference. So the radiative heat flux is sigma epsilon wall into T wall to the power of 4 minus T sat to the power of 4, okay, divided by T wall minus T sat. What you need to be careful is this sigma is Stephen-Boltzmann constant and not surface tension coefficient. So the value is 5.669 into 10 to the power of minus 8 watts per meter square, Kelvin to the power of 4. Okay, so this is actually the radiative transfer sigma, not the surface tension sigma. So this is the radiative heat flux, sigma epsilon into the temperature power 4 minus T sat to the power of 4. So this is coming from the Stephen-Boltzmann law divided by the T wall minus T sat. So basically you say H rad into T wall minus T sat is the radiative flux, and that is equal to this. So you calculate what is called the radiative heat transfer coefficient. So this, if it is less than HD, you can use the effective heat transfer coefficient, which will include both convection and radiation, can be written as H bar is equal to H bar D plus 3/4 of H radiation. Okay, and when it is of that order or bigger, then normally you use this expression, H bar is equal to H bar D multiplied by H bar D divided by H bar radiation whole to the power of 1 by 3 plus H rad. Okay, so basically what can be shown is that this can be simplified to this when HD is much less than H rad, then it becomes this. So that is the simplification that you can try and get. So this is the correlation. So when you get HD using the correlations that we had just written here for cylinder, for sphere, and similarly for other surfaces, you get that, and then you calculate the radiative heat transfer coefficient using this, compare them, and add the effect of the radiation heat transfer to get the effective Nusselt number by combining this and this. So this is the understanding of film boiling. So film boiling is important. So in film boiling, radiation is important, and you include radiation by accounting for it in this fashion. Let me complete by talking about flow boiling a little bit. Since flow boiling is complex, in nuclear boiling itself is complex, that you are not able to derive complete theories on it. So you are using experimental correlations. Flow boiling actually involves the flow and the turbulence that goes along with the flow, which is superimposed on top of nuclear boiling, and therefore is definitely substantially more complex. So Rosenau suggested that a good engineering approximation of heat transfer coefficients in film boiling, flow boiling, can be obtained by combining the convective heat transfer coefficients of nuclear boiling with the single phase convection heat transfer coefficient for that particular configuration. Say for example, if I am looking at flow boiling inside a pipe, then I can use nuclear boiling correlations for horizontal surface or a flow in a cylinder, because normally nuclear boiling correlations are usually independent of the geometric configuration. So you can use the radiative heat transfer, the nuclear boiling heat transfer coefficient as per, let's say, the Rosenau correlation, and on top of it, the force convection flow through a pipe, if the flow is turbulent, you use the Dittus-Boelter equation. So you calculate the heat flux because of nucleate boiling, and you calculate the heat flux because of force convection single phase flow of the same liquid, and you just add the two together. Rosenau said that gives you an approximation, which is good. So he says Q dot double prime in flow boiling is equal to, or is approximately equal to, if you'd like, Q dot double prime Q dot double prime wall, okay, which basically you can get based on whether it's nucleate boiling or film boiling from the expressions that we discussed above, plus Q dot double prime convective. Now this Q dot double prime convective is a single phase liquid flow convective heat transfer coefficient. Sorry, convective heat flux. It's not heat transfer coefficient, but it is heat flux. Okay, so what you're adding here is all in watts per meter square. So heat flux due to flow boiling will be the sum of the heat flux due to nucleate boiling or film boiling, that is boiling heat flux, plus single phase liquid flow heat flux due to convection. So this, Rosenau argued that it gives a reasonable approximation for various flow boiling configurations. And for pipe flows, in calculating Q dot convection, you use the Dittus-Boelter equation. We had derived this sometime back when we were looking at internal flows, internal turbulent flows. You get the Nusselt number as NUD is 0.023 into RED raised to 0.8 PR raised to 1 by 3. Okay, so this is the expression, or actually PR raised to N, which is 0.3 or 0.4 depending on whether it is heating or cooling. Now this 0.023 he recommends, Rosenau recommends, to replace it with 0.019 when you are using it in this equation for closer match with experimental data. Okay, so this is what we have for flow boiling. So flow boiling, there is not too much of theory or generalization possible. You either use CFD to compute, but even there the wall relationships should be derived only from these empirical correlations that we would normally be using, and there is no way that you can actually simulate this in more detail and get more accurate values. Okay, so this is where I would like to end the discussion on boiling and condensation. Okay. Yes, actually it's quite disappointing for those who are fond of very analytical correlations, very analytical mind, that you can write a theory and then use those theories and use various mathematical methods to get the expressions for heat transfer coefficient. But so far boiling and condensation, other than simplest cases of film condensation, have eluded that comfort, and therefore we don't have the possibility of getting those correlations in a simple form. So we depend on experimental data, and all-time greats like Rosenau, who have dealt all their lives with painstaking experiments and compilation of those data. We rely on their prowess of correlating the data and giving us the expressions which we could use. Okay. So we'll stop here with boiling and condensation. And with that, actually, we come to the close of what we wanted to discuss in the course on convective heat transfer. So just to sum up, we started with basic understanding of the governing equations in single phase convection. Then we looked at external flows, we looked at flow over flat plates, so boundary layer flows of forced convection. And we understood the various methods by which the problem can be solved. We looked at order of magnitude analysis for laminar, we looked at integral analysis, and we looked at similarity analysis, and we compared them. And we also understood how to simulate laminar flows using CFD and use that as a possible method. So you have a whole spectrum of methods when it comes to simple laminar force convection over a flat plate. And then we looked at laminar force convection inside pipes or inside ducts, and we understood the concepts of development and full development, and thermally developing and so hydrodynamically fully developed, that kind of flows, and we derived expressions for those. So in laminar flow, we were able to do all of that with absolute comfort, with not much of a problem. But the moment we went to turbulent flows, we had to understand what turbulence makes the systems behave like. And from that, then we looked at the various problems that we had looked at in laminar, the force convection over a flat plate. We looked at how the near wall flow behaves, how the core flow behaves, and then from that we were able to extract 2-layer and 3-layer models and power law models for doing integral analysis and getting the predictions for wall shear stress and heat transfer coefficients in turbulent flows. And we found that internal flows could also be treated by and large with the same exposure that we had to external flows. And in order to complete the understanding and discussion of all the analytical methods that we have available, we also looked at modeling of turbulence using different classes of turbulence simulation, direct numerical simulation. We talked about LES and we talked about RANS, the Reynolds averaged Navier-Stokes equations. And in Reynolds averaged Navier-Stokes equations, we looked at the Reynolds stress models, where you solve for separate components of stress, separate differential equations. And you looked at also the eddy viscosity models, in which we deal with single equation models, half equation models, 2 equation models. Okay, so those are the modeling components of turbulence that we looked at, and we understood how to implement that on software like Fluent. Then once that was done, we looked at natural convection. Okay, so we looked at laminar natural convection over a vertical flat plate, and then like a laminar internal natural convection and turbulent natural convection inside and outside. And with that, we ended the single phase flows, and the last 3 lectures we have looked at flows with phase change. We looked at film condensation in the first one, and we looked at dropwise condensation and correlations for film condensation in the second lecture. And today's lecture, it actually is almost a double header lecture, because now we are already almost close to 1.5 hours. We looked at boiling, the mechanisms of boiling, and the correlations of boiling. And with that, we close the course on convective heat transfer. I hope this gives you in a nutshell an understanding of how to approach problems in convection. We also approached it through models of physical insight, and also the models where numerical approaches can be used. So we looked at both of these in the current course. I hope this takes you to a better level of understanding of heat transfer and helps you deal with confidence the problems in convective heat transfer. Okay. We'll close the course here. Thank you very much.